Average velocity and instantaneous velocity using a graphical method. So we know this average velocity, it is defined as the change in the displacement upon time. Average velocity, we write V bar. This bar stands for the average, okay? Average velocity is equals to change in displacement, okay? Change in displacement or simply displacement upon time. Okay. Now if you consider the motions of a car along a straight line, and we take this line as the x-axis. This is the origin. Suppose at a time t1, the car is at a point P, and this car at this point is having a position x1. At a higher time t2, the car now is at a point Q and having a position x2. Therefore, average velocity is equals to displacement. What is the displacement of a car between this point P and point Q? Now the car displays from P to Q, right? So how much is that displacement? That displacement is equals to final position x2 minus initial position x1 upon time. What is the time taken for a change from P to Q? It is the final time t2 minus initial time t1. Or I can say this is equals to delta x upon delta t. Please note down here, this symbol, it is not a symbol for a triangle like you use in class 10. But this is a Greek symbol known as delta, and here this delta represents the change in quantity. Okay, now let us plot a graph for these situations of a car moving on a straight road. Now because I forgot to mention the velocity of the car that is moving on this straight road, let's say it is a variable velocity. So the graph, when you plot, it comes out to be like this curve. Okay. So this curve here, it does not mean the path traveled by the car. The path traveled by the car, it is always a straight line. But this curve represents the positions of the car at different time. Okay. Now this is a point P and this is a point Q. This point P happened at a time t1 and the position it is x1. This point Q happens at a time t2 and its position is x2. Okay, next. If you drop a perpendicular from this point P on this line, then you will get this point M. Okay. Next, I join the point Q and point P like this. You see with this, right, this blue line here, it is a straight line joining the point P and point Q. Now, let us say that this line PQ makes an angle theta with respect to the horizontal. Okay. Now, how much is tan theta? We know tan is equals to perpendicular by base. The perpendicular is MQ and the base is PM. Or, how much is MQ? This MQ here, from here to here, is the same as from here to here. Now, from 0 up to this point, this distance from here till this point it is x2. From here till here it is x1. So now only this distance it is x2 minus x1. So if this is x2 minus x1, then this distance mq also will be x2 minus x1. Similarly, pm will be equals to t2 minus t1. Okay, so this is x2 minus x1 upon t2 minus t1. Or I can say delta x upon delta t. Okay, now this delta x upon delta t, when you look back, it is what? Average velocity. So therefore, this average velocity, it is the same as this tan theta represents the slope of the line joining the point P and Q. So I conclude that the average velocity is equals to the slope of the line joining the point Q. Alright, next. Instantaneous velocity. We know instantaneous velocity is defined as the velocity at a given instance of time. Now suppose I want to calculate the instantaneous velocity, let's say at a time t1. At this time t1, how much is the velocity here? So for that, what I need to do is I have to reduce the this time interval delta t. Now if this t2 shift towards t1, let's say t2 is here. When t2 is here, then if you drop, right, if you draw a line from this point, okay, then you'll get a point Q now. It is shifting here, okay, and the slope of the line PQ, now it will be like a straight line, okay, like this. Next, again, if you further reduce the time interval by shifting T2 towards very close to T1. So when T2 is very close to T1, then delta T will almost be equals to 0. So we write delta T, this is tends to 0. So when delta T tends to 0, it means T2 is very close to T1, and when T2 is close to T1, then look at this point Q here. This point Q now will shift very close to point P. So this is a point P, and when T2 is too close to T1, then a point Q also it's almost coincident with point P. And the slope at that time, right? What is the slope? The slope of the line joining the point P and Q at that time, right, will approach the tangent, right? Or the slope becomes a tangent. So therefore, in the limits of delta t tends to 0, then this average value delta x upon delta t is known as the instantaneous velocity. And for that instantaneous velocity, we write with a symbol v. Okay. Or I can say the instantaneous velocity. Now for this limit, I will write it as dx upon dt. Okay. So when delta t is very small, then delta x upon delta t becomes dx upon dt. And this is known as the derivative of x with respect to time. Okay. And for that, you will learn in mathematics in the chapter of calculus. Okay. So this instantaneous velocity now, it is the derivative of displacement with respect to time. Okay. So this is how we calculate the average velocity and the instantaneous velocity for an object moving with a variable velocity using the graphical method.